Okay, so what we've been talking about primarily is electrostatics, in other words, charges that aren't moving. What we now want to talk about is electrodynamics, which is the study of electric charges in motion. And the first thing that we want to talk about is the difference between conductors, insulators, and semiconductors. So we all have a sense that metals are good conductors. Metals, in fact, are both good conductors of heat as well as conductors of electricity. And when we're talking about a conductor, what we mean is that the electrons inside the conductor are free to move. And that means that when connected to a source of electric energy, those electrons start moving and we get what we call a current, which we'll talk about more in a minute. Insulators are the opposite of conductors in that in an insulator, the electrons are tightly bound in the atoms, and so they can't move easily from one atom to another. So even if I take something like a piece of plastic and I connect a battery to it, no electricity is going to flow through that piece of plastic. And so things like plastic and glass are excellent insulators because they don't allow electricity to flow through them. There's another type of object or material, I should say, that's kind of in between conductors and insulators, and those are called semiconductors. And they're just a couple elements that act as semiconductors, and those are silicon and germanium. And the interesting thing about semiconductors is that they can be made to either conduct electricity or not conduct electricity. And that means that effectively they can be made into a switch. In other words, either it conducts electricity so it's on, or it doesn't conduct electricity so it's off. And it turns out that semiconductors are what are used inside computers. You may have heard before that a computer is essentially just many on-off switches. And those switches are actually made with silicon primarily these days. There's one other type of material that we want to talk about, which are superconductors. And it turns out that certain materials, when cooled to very low temperatures, like just a few degrees Kelvin, so way down in the temperature scale, when they're cooled that much, they have no resistance to electricity at all, meaning that electricity can flow through them with no resistance whatsoever. And we'll talk a little bit more about that later after we talk about the concept of resistance. Okay, so I've alluded to this idea of current, which is the flow of electric charge. So when electrons are flowing in a wire, we call that an electric current. The SI unit of current is the ampere, and oftentimes when we refer to current, we'll just say amps. So amperes is the correct term, but often we just will refer to current in amps. Now, what do I need to do to get a current to flow through a wire? Well, we need a couple things. First of all, we need a source of energy, and we call that electric potential. And electric potential is what we think of as voltage. So if you think about what does a battery provide or what does an electric outlet provide, it provides electric potential or voltage. The unit of voltage or electric potential is the volt, and a volt is equal to a joule per coulomb, so it's really an amount of energy per charge. Now the other thing besides a source of energy or a voltage that we need to produce a current is we need a complete circuit. So for example, let's say I have a battery here. So I'm just drawing a typical battery, and here I have a light bulb. In order to get that light bulb to light, I need electricity to pass through the filament. In other words, I need a current to do that. Well, in order to do that, what I would do is I would take one end of the battery and connect it to one of the connectors on the light bulb, and then go from the other connector on the light bulb back to the battery. And basically what now can happen is the electricity can flow through the wire, through the filament of the light bulb, and back down to the battery. So we have a complete circuit, and that's required if we want current to flow. Now, you can imagine that when I connect something to a battery or to the wall outlet, different types of devices will draw more or less current. In other words, if you plug a toaster into your wall outlet, it actually draws a lot of current. So does something like a hairdryer. But if you plug a radio into the wall outlet, it doesn't draw as much current. And what determines how much current a circuit will have in it is the resistance of the circuit. And resistance just is a property of electric components that tells how easily electricity can pass through them. So an example of that is a good conductor will have very low resistance, and an insulator has a very, very high resistance. Okay, so let's tie all this together. We've talked about current, which is the flow of electrons in a circuit. We've talked about voltage, or electric potential, which provides the energy to a circuit. And we've talked about resistance, which tells us how easily electricity can flow through a particular device. It turns out there's a law called Ohm's Law that relates these three types of things together. And Ohm's Law says that current is equal to voltage divided by resistance. So the more voltage, like the more batteries you have, the more current that you can get. On the other hand, if your circuit has a lot of resistance, then the lower the current will be. So we can see that current is proportional to the voltage and inversely proportional to the resistance. And we would write that as I is equal to V over R. Now obviously there are two other ways we could write that. We could write that just doing a little algebra as R is equal to V over I, or V is equal to IR. And so depending on what problem you're trying to solve, you might use it in any one of those three versions. But this is really the version that's kind of important to understand, because it's telling you that voltage causes current. In other words, you can't have a current without having a voltage. And it tells you that resistance is, the higher the resistance, the less the current that you get. Okay, so as we've said, current is measured in amperes or amps, voltage is measured in volts, and resistance is measured in ohms, and that's one I haven't mentioned yet. So the unit of resistance is the ohm, and amps we just write with a capital A, volts we just write as a capital V. The symbol for ohms is a little bit different. It looks like this. It kind of looks like an upside down horseshoe, and that's actually the Greek letter omega. So we use the Greek letter omega to represent ohms. Let's try out a problem. And this problem is going to use Ohm's Law, so let me just write it down here. So a toaster oven draws 10 amps when plugged into a 120 volt outlet. What is the resistance of the toaster? The first thing you want to do in a problem like this is identify what you've been given. So amps is current. So I know that current is 10 amps. Volts is voltage. So V is equal to 120 volts. And now I want to solve for resistance. So let me take Ohm's Law, and let me just kind of go through the algebra just as a nice review. I want to solve that for R. So I'm going to multiply both sides by R. So IR is equal to V. And now I'm going to divide both sides by I. So R is equal to V over I. And now I'm just going to plug in the numbers. So I have 120 volts divided by a current of 10 amps. And that gives me a resistance of 12 ohms. Okay, and so again, that symbol is the Greek letter omega, which stands for ohms. We've talked about power previously. Power is the rate of energy use. So remember, power is the energy used per time. When we're talking about a device that uses electricity, power is equal to the current times the voltage. So P is equal to I times V. Let's do an example and see how we do with it. So here's our example. A 60-watt light bulb uses how many joules in 5 seconds? Well, this question is simply trying to get at the fact that power is equal to energy over time. And to flip that around, we can see that energy is equal to power times time. So in this case, we have a light bulb which uses 60 watts. Remember, watt is the unit of power. And a watt, just to remind you, a watt is a joule per second. So you can see that if we multiply that by a second, we get to joules, which is our unit of energy. So we have 60 watts times 5 seconds. And if we work that out, we get 300 joules. So if you have a 60-watt light bulb burning in your house for 5 seconds, you've used 300 joules of energy. Okay, let's continue on. If plugged into a 120-volt outlet, how much current will the 60-watt light bulb draw? Well, we know that power is equal to current times voltage. So let me solve this for current. So I'm going to divide both sides by V, so P over V equals I. Okay, so that means current is equal to power divided by voltage, or 60 watts divided by 120 volts, and that is equal to 0.5 amps. Okay, so if you plug your 60-watt light bulb into your 120-volt outlet, it's going to use half an amp of current.